To start off with chapter 5, we're going to do an introduction on the normal curve. Your statistics book assumes you know normal curve. I know some of you may have seen this before and did some math with it, but we're going to do just a quick review, the worksheets on Blackboard Learn then, after we're done, of what the normal curve basically is. Okay, so this is a picture of a normal curve, also known maybe as a bell curve that you've heard before. And the bell curve, the mean is always in the middle, and that's the highest. Makes sense. Most people, most things should be average. And then the farther you get away from average, either increasing or decreasing, the less people or things that are going to be that. So think ACT, the average is 18. And the higher the score you get, less percent of students who score that. Both ways. Or the average number of calories someone consumes each day. The calories, right? Most people assume consume this many calories, and then as you increase calories, that's less people. As you decrease calories, that's less people. So bell curve often defines a lot of things in our society, what ACT score you need, SAT score you need, how often you need to change your oil, average oil life, a lot of things. So just to clarify, we are going to agree to use this normal curve. If you were to Google image normal curves, there's hundreds of different ones out there. Different, not so much different look, but instead of 34%, a different normal curve might be 34.1%. They vary a little bit, but we're going to use the same normal curve that the author of this textbook uses. Okay, so just so you know, if you just randomly Google normal curve, it might be little different percents. So all the answers in this book we will get from using these percents. Okay, so how do you read the normal curve? Like I said, average is always in the middle. And when you go left and right, this is considered one standard deviation from the mean. And we've studied mean and standard deviation. So if I go 1 unit to the right, that's 1 standard deviation from the mean. And if I go 1 unit left, that's also 1 standard deviation from the mean. So if I want to know what's within 1 standard deviation of the mean, I actually go both ways. This whole purple area is within 1 standard deviation of a mean, which would be, if I add those together, 68%. 68% of my data is within 1 standard deviation of the mean. And then if I go 2, here's 1, and then if I go 2, we say that's within 2 standard deviations of the mean, because I went 2 units both ways. And then 95% of the data is within 2 standard deviations. And then I go 3, and that's the most I go is 3, because anything more than 3 standard deviations is considered unusual. It's also defined as an outlier. So my graph only goes 3 standard deviations from the mean, and that would be to the end of those blues right there. Okay. So when you set up a normal curve, you always put the mean in the middle, add 3 standard deviations to the right, subtract 3 standard deviations to the left. And I'll show you what I mean by that with an example. Okay, so here's an example. Reaction times for a hand-eye coordination test administered to 1,800 teenagers are normally distributed with a mean of 0.35. That's important. I need to know what the mean is, and a standard deviation of 0.05 seconds. Okay, so once I know mean and standard deviation, I can set up my normal curve. So let's sketch a normal curve here. So in the middle, I'm going to put 0.35, right? You always put the mean in the middle. And then I'm going to count by standard deviations, and standard deviations is 0.05. So here's 1, so I'm going to add 0.05, and I get 0.4. Add 0.05, I get 0.45. Add a third one, and I get 0.5, and that's as far as I go. I only go 3 standard deviations. But then I also have to go to the left, and we know going left, you subtract. So 0.35 minus a standard deviation, 0.3, minus another standard deviation, 0.25, minus a third standard deviation, 0.2. Okay, so I have my mean in the middle, and I counted by my standard deviations both left and right. So then what I can do is I can put in the percents that I just showed you on that normal curve. So I can put in 34, 34, and then the next block was 13.5. And then I had 2.35. And then 0.15. Okay. Now that I have this normal curve set up, I can then answer some questions. My first question is, how many teens had a reaction time between 0.25 and 0.45? So on my normal curve, if I go from 0.25 to 0.45, that's everything within 2 standard deviations, which I can remember is 95%, or I can just add up those 4 numbers and get 95%. And I don't want to know percent. It's not asking me what probability of teens or what percent of teens. It's saying how many teens. So to get how many, I would take this 1,800 teenagers times 0.95, and that would tell me how many teens score that. So calculator, 1,800 times 0.95, I'd say 1,710 teens. Another question, what's the probability? So this is different. This one's saying how many. This one says what's the probability that a teenager selected at random had a reaction time greater than 0.4 seconds. So if I want greater than 0.4 seconds, I find 0.4 seconds, and greater than means to the right, and that would be add up those 3%. So add up 13.5 plus 2.5 would be 16%. And then that's just my answer, 16%. It doesn't say how many, it wants the probability. And probability I leave as a percent. Okay? Let's try another one. Ms. Chapman gave a test in her algebra class. The scores were normally distributed with a mean of 85 and a standard deviation of 3. You'll see this more when you go off to more of a collegiate level class. A test or quiz is given, and the professor will take those scores, do a mean and standard deviation, and create a normal curve, a bell curve. So most people are getting a C. So you have to kind of prove yourself that you're above average. So this is how they would do it. They would find mean and standard deviation. So let's put those in. 85 is my mean, so that goes in the middle. I'm counting by 3 this time because my standard deviation is 3. So 85, 88, 91, 94. And then I subtract 3, 82, 79, 76. Put in my percents. So I know this is 13, this is 13, not 13, 34, sorry. The next one is 13. And then we have 2.1535. Okay, so my question is, what percent, so it's percent now, what percent would you expect to score between 82 and 88? So 82 and 88, I add those together, 68%. What percent would you expect to score between 88 and 91? So 88 and 91 is right here, that's 13.5. what is the probability that a student chosen at random scored between 79 and 91? So 79 is here, all the way to 91 is there. I either add those four up, or no, I'm talking about 2 standard deviations from the mean, and within 2 standard deviations of the mean, we know is 95%. Okay, so those were all probability questions, probability percent. So I didn't have to, I could just look at the normal curve and just add it up. One more. Anyone that owns a car knows that your tires usually last around 30,000 miles. 30,000 miles, you need to buy new tires. That's how long the average tire lasts. With a standard deviation of 5,000. So there's my information. So let's create a normal curve here. So 30,000, and I'm going to count by 5,000s. So 35,000, 40,000, 45,000, and then subtract 5, so 25,000, 20,000, and 15,000. Okay, put in your percents, so you know 34, 34, 13.5, 2.35, 0.15. Okay. So it says, how many, now let's look at this question, how many tires will last between 25 and 35? So 25 and 35, we know is 68%, but it's not asking me for percent or probability, it's saying how many. So if I have 10,000 tires, and I know 68% will last that long, how many tires would that be? So I would need to take 10,000 times 0.68, which would be 6,800 tires. Okay. How many tires will last more than 40,000? So more than 40,000 is this. That's 2.5%. So I would take 10,000. 0.025, I need 2.5% as a decimal. And that would be 250, right? 10,000 times, yeah. I was second guessing myself, I don't know why. 250 tires. How many tires will last less than 25,000 miles? So less than 25,000 miles would be here, and then anything less than that, so I add up those three. So that would be 13, 14, 15, 16%. So 10,000 times 16% would be 1,600 tires. What is the probability that if you buy a radial tire at random, it'll last between 20 and 35,000 miles? So 20 and 35,000 miles is here. So I would take 68 plus 13.5. So 5, 11, 8, 81.5%, right? This is asking for probability, so I can leave it as a percent on that one. Okay, so that's the introduction. Some of you may have known that, some of you maybe have never seen this before, that's why I do it. So if you go to Blackboard Learn, you should see 5-1 worksheet right here. And then we'll get into the actual first section of Chapter 5 in your book.